It is my pleasure to welcome you to the crash course Quantitative Research Papers. We're dealing with the fourth section of a quantitative research paper, the methods section. And this part is about descriptive statistics. The basic idea of descriptive statistics is to describe a sample or a data set, to summarize what kind of data do you have there. The major types of descriptive statistics are frequencies, measures of central tendency, and measures of dispersion. And these three I would like to explain in this video lecture. Before I do this, a very important advice. A proper academic research paper in the realm of social sciences cannot only rely on descriptive statistics. There might be the odd one out, of course, but in virtually every case, you need inferential statistics. Descriptive statistics have the purpose to describe your sample according to socio-demographic and context variables. That is normally in all research papers the only purpose of descriptive statistics. Now, with this out of the way, let's dive into frequencies. You have absolute frequencies. That's just the number of times a value of a variable has occurred. For instance, here, age brackets from 20 to 29, 30 to 39, 40 to 49, 50 to 59. In our sample here, we have 200s in the first age bracket, 233 participants in the next, and so forth. When you have a project that is on the basic level of experiments, you use absolute frequencies. Normally, again, not in every case, but normally, you will always refer to relative frequencies. You can say it's just percentages. And the relative frequency is the ratio of an absolute frequency to the value of a value to the total numbers of values for a variable of observations. In other words, it's percentages. So the same what I've shown you here with absolute frequencies in relative frequencies in percent will be in the first age bracket we have 22.45%, then 30 to 39 years we have 26.15%, and so forth. You can of course combine two variables. Then you are doing cross tabulation. That's simply the combination of the distribution of two variables. Here is an example: gender, just female and male to keep it simple, and age groups. And here you can say 22.08% of all female participants are in the age group of 20 to 29 years, or 28.35% of all female participants are in the age group of 30 to 39 years, and so forth, and the same for the male participants. Frequencies you can use with every scale of measurement. Normally, you would use this only with this categorical scale of measurement. When you have a metric scale of measurement, you will come to measures of central tendencies. And these I would like to show you now. Three main measures of central tendency are the arithmetic mean, the median, and the mode. Most likely, if you have a metric variable, you will use the arithmetic mean. The arithmetic mean is the sum of all values divided by the number of all values or by the number of observations. You need, as a set, metric measurement level. The median is the value that separates the higher and the lower half of a distribution. You can do this with a metric scale, but at least an ordinal scale is required. The mode is simply the most frequent value of a distribution, and here you can start with nominal scale, with a nominal scale of measurement. In academic research, the mode is not often used. An example where it is important is an election. Let's take the UK. The party that wins the most seats in Parliament forms the government and has the Prime Minister. There the mode in the real world is very relevant. But in the academic world, in academic research papers, and especially with metric measurement level, normally you do not need this. You would refer to the arithmetic mean. I want to exemplify the three measures of central tendency with an example. Let's assume we have 9 participants and we've measured the age, 23, 27, 30 years old, up to 60 and then 75 years old. The arithmetic mean, I sum this all up. This is 405 and divide 405 by 9. So the arithmetic mean, the average age of our participants is 45 years. The median, the value that separates the higher from the lower half, in our case is 40. We can now say roughly half of our participants were 40 years or younger, and roughly half of our participants were older than 40 years. That is what the median tells you. And the mode is simply the most frequent value. In our case, we have 2 participants who stated they're 60 years of age, so the mode would be 60 years. Now the measures of dispersion. And here, it is not only to explain for descriptive statistics what you do with the variance and the standard deviation, but also to give you a foundation for inferential statistics. And more than this, an understanding of the idea of dispersion within statistics overall. And definitely all hands on deck. If you understand the variance and therewith the standard deviation, inferential statistics, which I explain the next part of this crash course, will come to you very, very easy. Very quickly, it will make very much sense, because all of the inferential statistic procedures that are based on metric variables, in their core, they're using some sort of variance. Furthermore, the variance, if you look now out of you, so the variance is the measure of a world in statistics. If you look out of the window, you see trees, grass, houses, other human beings, that is the world you perceive. That is your world at the moment. In statistics, the world is the dispersion or the variation of the data. The measure for this is the variance. So to understand the statistical world, you need to understand the variance. I will come to this and try to bring it closer to you in a moment. Here, just the definitions. The variance is the average squared difference of values from the arithmetic mean, whilst the standard deviation is the average difference of values from the arithmetic mean. I'll bring this closer to you in a moment, but let me give you the basic idea. Assume we have 2 countries, country A and B, and assume for simplicity reasons these 2 countries have only 2 inhabitants each. In one country, both inhabitants have an income of £50. In country B, one inhabitant has an income of £100 and the other of £0. If you just look at the arithmetic mean, you would say, oh, the 2 countries are basically the same. They both have an average income of £50. But if in one country everyone gets the same, that smells a bit like socialism. That can't be too healthy. In country B, with one has £100, the other £0, so one earns everything, the other one nothing, the other inhabitant. Also not the healthiest of countries. Civil unrest or even a revolution might be across the corner. So to understand data, and we need measures of dispersion. And to come back to my example, let's assume there are of course not 2 inhabitants in a country, but a few more. On the x-axis, that will be the income from £0 to a few million pounds. On the y-axis is the frequency, how many inhabitants of these countries have the respective income. From the example I've given you, country A will be the blue distribution. Country A will be the red distribution. Apologies, country A will be the red distribution. Everyone has something that's roughly close to the arithmetic mean. We don't have really poor people and we don't have super rich people. They're all roughly the same. From the example I've given you, country B will be the blue distribution. We have a few that are really poor and we have a few who earn a few million, who are really wealthy. We need a measure for this to see, do we have a rather homogeneous distribution? Are they all earning roughly the same? Or do we have a heterogeneous distribution? Are the difference in income rather large? This is where the variance and standard deviation come into play. Let me explain you the equation of variance and standard deviation. Here, trust me, don't switch up. Equations and math, these are our friends. They make our life easier. From personal experience, I can tell you, after I understood the variance and then there was the standard deviation, my understanding of statistics was so much easier and better. So stick with me. I'll give you another example of numbers. We have a sample of 4 participants, and we've measured on a scale, whatever scale it is, a 6, a 2, a 6, and a 2. So first participant said 6, second said 2, third participant again said 6, and the fourth said 2. The arithmetic mean in this case is 4. So we have an arithmetic mean of 4. You can calculate this 6 plus 2 plus 6 plus 2 divided by 4, but here I believe you can intuitively see it is 4. Now, if we can see here, this is simplified data, of course. We can see, all right, the dispersion is 2 up, 2 down. So the measured values are either 2 higher or 2 lower than the arithmetic mean of 4. But with a more complex and larger sample, we cannot see this intuitively. So we want to have an indicator, a measure that tells us how do the values differ from the arithmetic mean. At first glance, one could say we just formed the difference of xi, our measured value, and the x average, the arithmetic mean. So measured value minus arithmetic mean, and we sum this up. In our case, that would be 2 plus minus 2 plus 2 plus minus 2. And that equates to 0. It doesn't matter what kind of data you have. If you apply just this equation, you will always end up with 0. So this first idea does not work. But there's a trick in mathematics, and that is minus times minus equals plus. So we simply square this difference. We still have the difference of the measured value, xi, and the average value, and we square this. We do this in our case. It is plus 2 to the power of 2, or plus 2 times plus 2 is 4. Minus 2 squared, minus 2 times minus 2, minus times minus is plus. We have 4. 2 squared again 4, and again minus 2 times minus 2 is 4. So we come up with 16. And what I've done here, this equation is in the numerator of the equation of the variance. Now we divide our 16 that we have by the number of participants. In our case, it's 4. So 16 divided by 4 is 4. And that is the equation of the variance. Now we have a variance for these data of 4. Here we can clearly see, wait, 4, the values are not 4 higher or lower than our arithmetic mean, they are 2 higher and lower. And this is, we run out of our range or our scale because of our math trick to get rid of the minus, the squaring. Now the second trick of mathematics comes into play. The counterpart or the antidote to squaring is the square root. In our case, we have the square root of 4, which equals 2. And that is the equation for the standard deviation. And now we can say standard deviation of 2, our values will be on average 2 higher or 2 lower than our arithmetic mean. Here we can clearly see, yes, happy days, that is correct. With a simplified data set, this is 2 higher and lower. That was the standard deviation. Once again, and now watch this again. If you have understood the variance, you have understood the core, one of the cores, the foundations of statistics, especially inferential statistics. Speaking of inferential statistics, that will be the next part in this crash course, and I hope I could give you now a good foundation by explaining descriptive statistics. Till we meet again and dealing with inferential statistics, I wish you all the best, and it is bye-bye for now.